During the first part of the lecture of today, I will present some results concerning the sectional curvatures of the model spaces, that is, the Euclidean space, the spheres, and the hyperbolic spaces. Let's start by observing that if a Riemannian manifold is a frame homogeneous, then there's a constant sectional curvature. This lemma is very easy to prove, and the reason is that when you want to prove that the sectional curvature is constant, you have to prove that for each two-plane the sectional curvature does not change, but by hypothesis the Riemannian manifold you are considering is frame homogeneous, so there exists an isometry sending a two-plane at P to any two plane at Q, where P and Q are arbitrarily chosen. Now, since the curvature tensor is invariant under the action of isometries, you have that the sectional curvature of two-plane at P will be the same as the sectional curvature of any other two planes at Q. Now we want to use this lemma to prove this theorem, sectional curvature of the model spaces. This theorem says that the Euclidean space Rng bar has constant sectional curvature 0. It says also that the spheres of dimension n and radius r equipped with the standard metric have a constant sectional curvature 1 over r squared, and the hyperbolic space has a constant sectional curvature equal to minus 1 over r squared. The reason why the lemma applies in this case is that we know that these three manifolds are frame homogeneous, so it is enough to compute the sectional curvature at one point. I will not present the proof, I leave the details to you. Instead, what I want to do is to say something about this proposition. A Riemannian metric G has a constant sectional curvature equal to Z if and only if its curvature tensor satisfies this identity. Rm equal 1/2 C times the product, the Coulomb-Miseau product of G with itself, and in this case it is easy to prove that the Ricci tensor is given by n minus 1 times C times the metric, where n is the dimension of the manifold and the scalar curvature is just n times n minus 1 times C, and the Riemann tensor, the Riemann curvature endomorphism is given by this formula. R VWX is equal to a constant C times the inner product of W and X times V minus the inner product of V and X times W. Equivalently, if you use the components, this formula here becomes Rijkl equals C times GIL GJK minus GIK GJL. and the Ricci tensor has components equal to n minus 1 times C times Gij. If you want to prove this proposition, this implication is easy, it's just a computation. It's easy to prove that if this is true, or equivalent, this is true, the sectional curvature is constant and equal to C. The problem is how to prove this implication. And in order to prove that implication, you have to use proposition 8.31, which says the following: suppose that R1 and R2 are algebraic curvature tensor on a finite dimensional inner product vector space V, then if for every pair of linearly independent vectors VW in V, you have that R1 VW over square of the length of the cross product of V and W is equal to R2 VW over square of the length of the cross product of V and W, then R1 coincide with R2. I want to say something about the hypothesis. What is an algebraic curvature tensor? An algebraic curvature tensor is a covariant 0,4 tensor having the same properties of symmetry as the Riemann tensor, the 0,4 Riemann tensor Rm. So in order to prove the proposition about metrics with constant sectional curvature, the idea is to use this lemma comparing Rm VWW V over the length, the square of the length of the cross product of V and W with 1/2 C Cool-Cardinal-Mizu product of G with itself, evaluated at VWW over length of V square. So you know that this is a sectional curvature. By hypothesis, this is constant. A computation shows that this is also constant, so they are equal. And this implies that the Riemann tensor is a 1/2 C G Cool-Cardinal-Mizu product of G by itself by this lemma. And the statement about the Ricci tensor and the scalar curvature follows from the definition. You just take the trace of this, or if you want, you can work with the components. So if you have proved that this is true, then you have also that Rijkl, this is C times GILGJK minus GIKGJL. And from here it's easy to prove Rij equal n minus 1 CGij, which is equivalent to this. And this is immediate. And why this is true? This follows from this formula, for example, or this one, as you want, because what is Rm of VWX Z, this is RVWX Z. So the formula that you have to prove is this. So you have just to convince yourself that this is true, but this follows from here, for example. It's enough to prove it for a basis of element of the tangent space at a point. Okay, now we change topic and we talk about Jacobi fields. Our goal is the following. We have proved that geodesics are locally minimizing curves, and we have seen, for example, what happens on a sphere if you consider the point P to be the North Pole. Then the geodesic passing by P is this great circle, and it is clear from the picture that this geodesic is not minimizing beyond the point Q equal to the South Pole. So this sentence means that if you take a point, for example, here or here or here, the segment of geodesic having endpoints P and Pi is locally minimizing. It is not true if you take a point here, because the piece of geodesic which is minimizing is this one. And not this one. What we want to do is to give a deeper look at the minimizing properties of geodesics, and we will prove that if we define variation fields of spatial variation of curves, we will see that there is a correspondence between the zeros of these spatial vector fields, known as Jacobi fields, and the points beyond which a geodesic is not minimizing. So let's start by giving some definition. So suppose that I, K are intervals. Suppose that gamma is a geodesic in a Riemannian manifold of dimension n. Then we can define a map K to be a variation of gamma as did in the past. What is new is the following. Gamma is a variation through geodesics if each curve gamma st equal gamma st with s fixed is a geodesic. Now I want to determine the equation satisfied by the variation fields of a variation through geodesics. This equation is known as Jacobi equation, and its solutions are known as Jacobi fields. So suppose that gamma is a geodesic, J is a vector field along gamma. If J is the variation through geodesics, then this is true. How to prove that the field, the variation field J satisfies Jacobi equation? So we start by writing T as T to be derivative with respect to T of gamma at St, S as T, delta S, gamma St. Then we use this hypothesis. And then we have that the covariant derivative of capital T is identically 0 for all values of S and T. Consequently, also this is 0. Then we use proposition 7.5 to reverse the order of these covariant derivatives along gamma. So we have that 0 is equal to ds dt t equal to dt dst plus rst t. But now we can use also the symmetry lemma, which has been proved in the past. If I'm not wrong, is the result 6.2, and you get that this is true. And then what we have to do is to evaluate at s equals 0. Then you have that s 0t, this is jt by hypothesis, and T0T, this is gamma prime T. And clearly you get this identity. So we found a differential equation. Precisely, it's a system of differential equation. And as we did in the past for the parallel transport equation or the geodesic equation, we have to state a result about the existence and the uniqueness of the solutions. So suppose that as before gamma is a geodesic, suppose that A is a point of I, P is gamma A, then for every VW in TPM there exists a unique Jacobi field that is a solution to the Jacobi equation along J along gamma such that J at A is V and TTJA is W. How to prove this result? So choose an orthonormal frame which is parallel along gamma, and then you can write V and W as VI EI at A and W equal WI EI at A, and gamma prime T equal YIT EIT. So we have to now write down J in terms of EI as follows: J of T equal JIT EIT, and if you do this, you can express dt square J plus Rj gamma prime equals 0. as follows: j second I t plus r j k l I at gamma t times j t y k t y l t equals 0. So this is a system of n linear second order ODE where the known functions are ji defined on I with values in R. As we did for the geodesic equation and the parallel transport equation, we want to write down this system in terms of first order ODEs. So we introduce an auxiliary variable. So we set wi equal j dot I, and we get the system j dot I equal wi, w dot I equal minus r j k l I gamma t gjt ykt ylt. Now what we have to do is to use the theorem of existence and the uniqueness of solutions which are smooth on the entire interval I with initial conditions JIA equal VI and WIA equal WI, where VI are the components of V with respect to this basis, and WI are these components here. The reason why this second equation is compatible, is equivalent to dtja equal w, follows from the fact that the dtja is j dot ia EIA, and this is WIA EIA, but this is exactly W. So if this is true, this is satisfied. And we get then the existence of a unique solution J such that J at A is E and dtj at A is W. Using this result, it's easy to prove that if J gamma containing key gamma denote the set of Jacobi fields along gamma, then J gamma is a 2n dimensional linear subspace of key gamma. Why this is true? The linearity follows from the fact that the Jacobi equation is linear. The fact that the dimension is 2n is that to uniquely determine a Jacobi fields, you need a pair VW of elements of TPM. Since the dimension of the manifold is n, then you need 2n in total, 2n components to determine V and W, and this means that this space depends on 2n parameters, that is its dimension is 2n. The next result is a proposition which is the converse of theorem (10.1), because it says that if we have a Jacobi fields along a geodesic, then we get some information about the behavior of some families of geodesics. Actually is a proposition if M is complete or gamma is a geodesic defined on a compact interval I, then every Jacobi field along gamma is the variation field of a variation through geodesic. So in other terms, if J satisfies the Jacobi equation, then J is the variation field of a variation through geodesics. Instead, theorem 10.1 said that if J is the variation field of variation through geodesic, then it is a Jacobi field that is satisfied the Jacobi equation. Okay, how to prove this result? So suppose that J is a Jacobi field along gamma. Up to a translation, I can assume that 0 belongs to I, this interval here, and then I can set P equal gamma 0 and V equal gamma prime 0. So this implies that my geodesic is given by this formula. Okay, now we choose. So essentially, the goal of this proof is that we are given a geodesic gamma. We have to show that there exists a variation through geodesics whose variation field is J. So now we choose a smooth curve sigma a smooth vector field along sigma satisfying the following identities. Sigma 0 is P, sigma prime 0 is J at 0, V at 0 is V, sorry, ds V at 0 is dt J at 0. In this formula, this is the covariant derivative with respect to sigma, along sigma, and this is the covariant derivative along gamma. So now we define a variation writing gamma as T it is clear from the hypothesis that this map is defined at least for St in minus epsilon epsilon times I. This follows from the fact that M is geodesically complete, or from the fact that the interval I on which gamma is affine is compact, and this means that the domain of the exponential map is an open subset of Tm that contains the compact subset PTV with T in I, and this means that there exists a number epsilon such that this map is affine at least on minus epsilon epsilon cross I. So it follows from here that gamma 0t is an exponential map at sigma 0 tv0 equal exponential map at p of tv equal gamma t, and we have that gamma s 0, this is exponential at sigma s of 0, and this is sigma s. So this means that this says that capital gamma is a variation of gamma, and the fact that capital gamma is defined through the exponential map guarantees that also when s is not 0 but is fixed, this is a geodesic, this defines a geodesic, and this means that we have a variation through geodesic. If this is true, then Wt equal delta S gamma 0t is a Jacobi field along gamma. Our goal is to prove that W and J coincide. So in order to prove this, we look at W0 which is given by the derivative of sigma at 0, which by hypothesis is, by construction, is J at 0. In a similar way, you can prove that this is true. We will see this in a moment. So suppose that this is done, then existence and uniqueness of Jacobi fields implies that W is identically equal to J, and this is the end of the proof. So it remains to see why this is true. So we look again at the formula for gamma st. This is the exponential at sigma s of t vs. From here you get that the derivative of gamma with respect to t evaluated at s0, this is equal to this. We use the symmetry lemma and get that this is true, and we use this for proving that we can exchange these two derivatives and get that this is true. So this is exactly what we needed, is this identity, and so we are done. Let me check how much time I have. Okay. I'm going to introduce two classes of Jacobi fields, precisely tangential and normal Jacobi fields. In order to do this, we observe that if I give you a geodesy, then it's possible to write down immediately two Jacobi fields. One is denoted by J0, and it is given by this simple formula. The second is J1T, and it is given by T gamma prime T. The proof is immediate. You just replace the expression for J0 and J1 into the Jacobi equation, and you will get the identity. If I is compact, I is this interval, or M is complete, then J0 is the variation field of the variation gamma st equal gamma s plus t, and J1 is the variation field of gamma st equal gamma 1 plus s times t. In order to prove this, you just to make a computation. So given a regular curve in M, we can define T gamma T M tangent as the one-dimensional subspace of T gamma Tm spanned by gamma prime T, and T gamma T orthogonal M as its orthogonal complement. A tangential vector field along gamma is a vector field V in K of gamma such that V at T belongs to T tangent gamma Tm for any values of T, and a normal vector field along gamma is a vector. No, let's write. It's okay. A vector field V in T of gamma such that Vt belongs to T orthogonal gamma T M for any value of T. The space of tangential vectors is denoted by K tangent gamma, and the space of normal vector field along gamma is denoted by K orthogonal gamma. It is clear from the definition that normal Jacobi fields field is singular, J along gamma satisfies Jt orthogonal to gamma prime T for every value of T. If gamma is a geodesic, then we use the notation J orthogonal gamma, J tangent gamma as the space of normal Jacobi fields along gamma and space of tangential Jacobi fields along gamma, respectively. Now we start to look at the properties of Jacobi fields which are zero at some point. We have the following proposition. Suppose that J is a Jacobi field along the geodesic gamma. Then we have the following equivalent statements. A, J is normal. B, J is orthogonal to gamma prime at two distinct points. C. J and DTJ are orthogonal to gamma prime at one point. DJ and DTJ are orthogonal to gamma prime everywhere along gamma the trick for proving this proposition consists in defining a function writing f of t equal inner product of jt and gamma prime t, and proving that f is an affine function let's first show that this implication is true, and then we will show that these statements are equivalent. So we observe that f second is a dt second j gamma prime. Here I am using the fact that gamma is a geodesic, so there is only this term which is sorry, this is a t. So I was saying I'm using the fact that gamma is a geodesic, so there is no derivative, there are no terms involving the derivative of gamma prime. But since J is a Jacobi field, this is equal to minus R J gamma prime multiplied with gamma prime, that is minus 0,4 Riemann tensor evaluated at J gamma prime, and this is 0 because the last two entries are equal. So we have a function having second derivative equal to 0, consequently is an affine function. So now how can we prove that these four statements are equivalent? If J is normal, then we have that F is identically 0. but f is an affine function, and an affine function is identically zero if we know that f is zero at 2 points. So A is equivalent to B. Now we observe that f prime t is given by dt j t gamma prime t, and this is zero if and only if dt j t is orthogonal to gamma prime t. So ja and dtja are orthogonal to gamma prime a, if and only if f at a equal to 0 together with f prime a equal to 0. So this says that f identical 0. So we prove that C is equivalent to B. Now J now sorry, if now I know that f is equivalent to 0, then I have that also this is true, and this implies that J and dtj are orthogonal to gamma prime t for every t, and this was a statement D. So it is done. How much time I have? Okay, I think is a good point where to stop. Thank you.